And what do actuators do for us?
Work.
Well, there's a lot of things that does work, but actuators do certain type of. Motion, yeah. So it converts power source into motion, right? And then we have two types. We have linear actuators and we have rotary actuators. And then we have motors. So motors are rotary actuators, but they've been around so long they got their own. It's like the original operating system for these computers was called a disk-based operating system, or DOS. Well, every operating system after that has been a DOS, right? I understand 90% of them. But DOS has its own unique name. We have a position sensor called a limit switch. And then we got another term called proximity sensor. But a limit switch, and that's when it senses when something's at a certain spot. Yeah, but it's a proximity sensor, but it's been around so long it's got its own name. So when we use the term proximity sensor, we're usually talking about electronic, solid state sensor that sits when something's at a certain location. So so motors, even though they're a rotary actuator. So usually when we talk about a rotary actuator, we're talking about an actuator that has an internally limited stroke, right? And the stroke of rotary actuators are given in degree, where the stroke of a linear actuator is given in length, like inches, feet, millimeters, stuff like that. The rotary actuators would say it has like a 180 degree stroke. That means it would be able to just do a half. And these are limited inside the rotary actuator. I meant to take some videos of the rotary actuators we have on our manufacturing line over there, but I got busy on another class. And did that. But we talked about single acting cylinders, rams. Y'all know what a ram is? What's a ram? The bolt, right. They're using single acting cylinders. These guys are heavy lift guys. Then we talked about different ways of mounting, and that's one I brought over. We had some of these. We have we've got a trunnion mount over there, but I didn't bring it over. It's a variation of the cap-in trunnion. In fact, it is a trunnion mount. We'll go over and look at it, but this is a hydraulic cylinder. I think probably weighs 50 pounds. And plus, it's hydraulic, so it's kind of greasy. The ones that I have up here is I have a cap flange, which would be a rectangular cap flange, which would be a real long one. Right there. See the mount on the back there? So that's a rectangular cap flange. And then I have one that's basically two types. It's a centerline. It's a centerline lug. It's got two. Don't look at the pressure hole. Look at the mount. That's the pressure hole. Here's the mount hole. Well, we got two ways we can mount this one. We can mount it on the captain. The captain mount. And then we got, it's not called a center mount. It's called a dual center line mount, I think. They don't show it. I thought they did. Well, one of them is basically a centerline mount. So the screws on the side. These are head end mounts. Then we have a cap end mount. A rod end mount. And then we got one of these right here. We have a side end angle mount, right? That should be that one. And I thought we had one of these over there, a side load, but I didn't see it. Oh, here we go. Side tap hole. So that one that's got the 2 holes on it, that would be called a side tap hole. We got 2 of those. And then we got one which would be a cap in. This one right here can be both. This one. That one. Right.
You said because even though both sides are capped, you prefer this to head and this to cap.
So the end that the rod comes out of is referred to as the head, and then the other one's referred to as the top. And of course, the nice thing about these rod type frames is that these are easily repaired.
So you replace it, it's coming to replace all
You'll probably have to get, I'll get you out from the manufacturer. I think it's exactly the right seals and everything to come with.
You have to have a print.
Not on those. Those
Not
are,
on these?
but they've got the seals on the inside. And then we don't have, I don't know about the double acting cylinders we have, but some of them are screwed. So you put in a device and you can break it loose and screw off the cap.
We haven't got to
And
this
then
one here
one
yet.
time,
We haven't got to this
yeah.
We got to the mount, out of mount.
yet. Down.
It's a proportion. Wow, that's an expensive.
Look,
Yeah. So proportional valves like this, we can control how far it goes. We can control how fast it goes, so we can make it go at a precise rate. And speed back, so it actually sends back to your controller how fast it's going. Proportional valve systems are very expensive, but in some situations for precision, they really got to work. So if we had the fluid power actuators on a robot, it would have to have that type of situation. Unless it's what we call like a bang robot that just moves between ends. We can have a pretty accurate robot just by running it up against something. We call them hard stops. The only problem you got is over time your hard stops start wearing off and the accuracy of your robot is away. If you got to have basically an infinite number of positions that you go within a volume, then you're probably going to use an electric robot because you can put that sucker anywhere within a volume. And we're talking about repeatability that's just unbelievable. I think we talked about that in this class the other day about using your signature. Well, a robot like that will do it exactly the same way with precision that we don't understand. And we refer to it as repeatability. We talked about that, talked about cushions. Talked about how they work. I'm not sure about our, I don't think our single acting cylinder, it looks like it's got cushions on the thimble, but it didn't have a variable across it. Now the symbols we have in our lab don't exactly match what we're using. And Franklin brought that up. He was looking for in the diagram he was supposed to hook up. He was looking for one without cushions because the one on the diagram didn't show cushions. But that's all we got to do these labs. And I think what we left off with was controlling the speed. And then we talked about these different formulas. There is one place, I think in one of the tests that I require you calculate this, but I give you the formula. You don't have to look it up. So all you got to do is get used to and a lot of people don't understand how we split things up on a calculator to tell it to calculate certain sections before they do that. Now, so what you would do up here, if you're gonna enter this into the calculator, and this is a standard entry calculator, which most people have, is if you're dealing with hydraulics, we're dealing with pneumatics, so we'd use this one. So first of all, what we would do on our calculators, we'd take 28.8, and then we'd hit the times key, and then we'd enter our cubic feet per minute. Let's say 9.9. Okay. And then what would we do? Well, then we would hit the what? No, we'd hit the equal key. Okay. I'm sorry, you're right. Do it. Then we would hit the divide key, whatever it is on your calculator. Then what would we do? Then we'd open up parentheses. And then we'd enter the area, right? And so we'd do d squared times 0.785. And then I'd close my parentheses, and then I'd do this. A lot of people don't know how to use that parentheses key to do those bottom numbers. Y'all know, y'all okay on that? We talked about meter in, meter out. Do you have any questions on those? So what does meter out mean? These diagrams here came out of another book, and they're not drawn exactly to industry standard. But what does meter in, meter out mean? Well, when we meter, what does that mean? Metering. Control the what? Well, we control the speed by controlling the flow. So meter means, and so what we're doing is we control the flow. We can either control the flow on the input, right, of the cylinder, or we can control the flow on the output. If we control the flow on the input of the cylinder, that's called what? Meter in. Okay, if we control the flow on the output of the cylinder, or the exhaust, or the tank, or the return on the hydraulic system, we call that what? Meter out. Meter in, we use these for positive loads. Can't control negative loads. Y'all understand what those terms? What's negative load?
You held your hand up and then it's flat.
Yeah, so it'd be your cylinder mounted this way, or like this way, or not, or mounted past center, right? So if we mounted that thing past center, then all of a sudden our loads are going to be negative. The prime mover is always operating against the maximum pressure. So this would be meter in. And then meter out, what we do here is we put our flow control between the exhaust or the reservoir of a hydraulic system. Okay, now provide accurate control of positive and negative loads. The prime mover always operates against a back pressure. So that's what we're generating. We generate that back pressure. So compressed air won't uncompress or won't. And of course, when we use single acting cylinders, we have to meter in. And when we use double acting cylinders, we have to meter out. All right, okay. Everybody okay? And we can control, so what we do is we use these one-way flow control valves. Somebody brought this up the other day, so, and they were right. So when we draw our flow control, our directional control valves, so our valves and our actuators are usually drawn horizontal, right? I understand that. And we'll start down at the bottom with our power source, and then we figure out which is the normal position of the valve. Up if he's in here right. And then what we would do here is we do what? We'd swap them around and then we'd put the exhaust over here. Right? I probably need to look at some. And they're supposed to touch. So these supposed to touch. And then what do? We number it according to where it's at in its normal position. In fact, this is not right. I'm thinking I got a normally closed, normally open valve in my head. So if this is 1, this will be 2, right? I'm sorry. Because 1 comes in on the center, so this is 1. This will be 2. And then we'll have, right? And then over here, what would we do? So this one would, this would go straight up. And this one would come down to, oh, sure. So pressure comes up, so 1 would be right here, right? And this right here would be what? 2. And then this right here would be what? 3. And this right here would be 4. Right? So what I gotta do is I gotta take 4 to my exhaust. No, this would be 1, 2, 3, 4. Huh? So this would be, hold on a second. I got it now. I'm trying to do a 5-way valve. So this would be 1, right, 2, 3, 4. Right? The exhaust is on the other side. I might have to look this up, guys. My head's going crazy. So what we need is we need a if we're going to control a double acting cylinder, we need either a 4 or 5-way valve, right? So I think we're using a 5-way valve. So I had it right first time. I got myself confused. Huh? There we go. 1, 2, 3, 4, 5. That's it, right? Of course, I numbered my things. And oh yeah, there you go.
They're small on one side, like
What do you mean all on one side like that?
Like, you only got them all in that first lot.
That's where they all are. I don't know what you mean. It's just I got to put the numbers. So if this is the normal position, I would extend these up, right? And this right here would be 1. This right here would be what? 2. So I come over, and I come down, and then I would come up, right? Right? There you go. What I've done is, for y'all, to keep y'all from having to go into these books all the time. And, of course, you still don't have the pictures, but these are all the valves available. So what this means is some of y'all might want to work on these at home, and y'all cannot carry these books out. Okay, so what this does is this is going to give you all the valves that's available in the Festo kit. So that means you can carry one of your labs home, especially some of these that you want to design. Now you know the parts that's available. What happened to us is last time I taught the class, when we had that last assignment, it was at home, and people brought back circuits that they had designed with parts that we don't even have.
Yeah. Do we have that flexibility?
No, you don't have that flexibility. Not unless you find the part yourself and you buy it and you bring it in. You can port it up to Festo. That would be fine. So, no, you don't have that flexibility. So, and what this came about, by the way, is that, so everything is drawn, what? All your valves are drawn, and also your actuators are drawn horizontal, right? And there's only 2 valves, and somebody brought this up the other day. I can't remember who it was. The only 2 valves that are drawn vertical are your what? Your flow control valve. And we'll use this symbol right here, basic symbol right there. Even though you got to understand. So that I could legally use this symbol right here, which I don't like. And that's what they call the simplified symbol. They only draw the head on. So, what we got to do is we know what valves we have, and we know what pistons we have, and we know we got a couple of double act. I think we got 3 double acting cylinders, right? Available to you. I think we got 1 single acting cylinder, and I think we got 3 double acting cylinders. So the only thing that we can really draw, and which direction which side you put your flow control valve, guys, it makes no difference according to the symbol. You just don't want them crammed into each other. So normally we draw those going out. So on this side, I would do what? Not a U, a V, right? We got a yeah, a V. And then we would make sure we put and ours are variable flow control valves. And this is
like you can draw a flow on the outside. The variable, it can be pointed left or right, at an angle.
No, usually what we do is we draw the flow control in series with the pipe, because the pipe goes through the flow control. And then what we do is we come over here. Let me get over here so I can make it a little cleaner. So what we do is we got our cylinder, and then we come down with this. Now it might, and then what we do is these are going to come down, and then we're always going to put our flow control in this line right here. What do you mean to the right?
You know,
The arrows?
Yeah.
Yeah. Now then, when we come over here and we put our check valves, we come over here and we put them going out away from the cylinder, because I got my cylinder drawn real big, right?
So I guess what I was asking, if I draw my arrows going the opposite way, does that mean the flow going the opposite?
No. And now what you're supposed to do, though, technically, we're supposed to do this. Which means what? Yeah. Equate in one unit, yeah. And dashes. This would be the way flow control valves. So your actuators are horizontal. All your valves are horizontal. Your pipes are going to be straight line. And if you do need to turn them, you're going to do it at a 90-degree angle. You know. And then we looked at bleed off. Bleed off used a lot in the bleed off picture is gone. Good gracious. But what we do with bleed off is we bleed it off. It's using hydraulics and send it back to tank, right? Everybody understand that? The picture's coming out of the power plant. So what we would do on a bleed off to control the flow is that we would literally take it and then send it to a flow control, and then it would go back to the tank. So what you're actually doing is you're deliberately making the flow split. And if the flow splits, then your actuator's going to get less flow, right? And we refer to this as what? Bleed off. I don't know what picture went. So this would be the actuator. Selecting the cylinder, I think we talked about this. We want at least 25% to allow for friction to move the reach. Now, there's a lot of math to calculate how much force that you want, because what we've done every time when we've been calculating force, we've been putting our load like this. If we're saying we're trying to move a 200-pound load or something like that, that's it sitting on the cylinder this way. But as soon as you slide that thing across something, you do it at an angle, right? So the least friction I would have, or the least weight I would have, is when it's laying horizontal. But as soon as we start to go up on the incline, then the more weight, more force we're going to generate until it gets vertical, right? That makes sense. Selecting cylinder using surface and power. Is this in your book, or did I pull this from somewhere else? They don't give a table number on it, so I got my book up here, but it would be inside this section. It's in there. No. It's not a big, huh? But it makes sense. It estimates the force for 900 pounds. So what they do, you see how they come up with something called watt? Okay, so they say, well, I want to move a 900-pound weight at 80 psi, and that would be a power factor of 11.25. So what size score would I do? It's a pretty easy formula. I mean. 4-inch board. Let's see how it came over. See how my guy came over that. Yes, no. Yeah, so all you do is you take the force, you divide it by the pressure, and this comes up with a number. That number comes up, and they call that the power factor. And then what you can do is you can just look up the power factor and choose the next highest, right? That makes sense, right? That's one of the easier ones, isn't it? Bore versus force. So this is a good chart. This is in y'all's, this is 4-1. In fact, the data book that you got is better, the digital data book, because it's got all kinds of, so if you got your digital data book, anybody got the data book yet? Oh my goodness.
Yeah, I try to get it.
I don't know what to tell you. Well, it depends on page 15. I mean, I only got one set. I could let y'all watch.
I got no book. I just.
Did you look on with Franklin?
We got hydraulic cylinder force.
Yeah. So hydraulic cylinder force. So what's so neat about this? We know that force is equal to area times pressure, but what's nice about it is we have these standard size rods. I mean, we have these standard size cylinders. So when I come over here and start looking, let me yeah, so when I come over and start looking at this thing, let me blow it up so we can see it a little better. So I'd say, okay, what force? Let's say I've got oh, these are speeds. Gosh, dang, wrong table. Here we go. So let's say I've got a 3-inch rod. Let's say I've got a 3-inch bore with a 1-inch rod, and I'm running at 2,000 psi. Well, all I have to do is come over here and find 3-inch, and this would be 2,000 psi. So I would be able to generate 14,137 pounds of force when I extend. Yeah, 2,000 psi. So I'm right here. Y'all see that? Yes or no? 14,137. Now I could take my calculator and I could do the math. I could find the area of a 3-inch rod. I could, diameter squared times 0.785, multiply it by 2,000, and it would come up and give me 14,130 something pounds. Or I could look it up in the chart. Which one's easier? Okay. Now let's say it's got a 1-inch rod. Well, I drop down right below that, and it says, well, this guy can generate 12,566 pounds of thrust when I retract. I mean, force when I retract. So now I don't have to do all this math, right? You understand? I don't have to take the area of the bow. I don't have to take the buoy area, subtract the area of the rod, multiply that times the pressure to get how much force there is. Right? You understand? And even if we give you something that doesn't fall in, even if we give you something that does not fall exactly into this, you would still be able to know right off the bat if you're right or if you're wrong, right? You understand? So if we got it like which is pretty neat. So this has a 1.5-inch rod. So what would be the force on a hydraulic cylinder I would be able to generate if I had a 4-inch bore and and a 2.5 inch rod at 3,000 psi. 4-inch bore, right? 3,000 psi, right? So extending, okay, then I would look at, what did I say, 2.5 inch bore? 2.5 inch rod, then I'd drop down and I'd say, well, 2.5 inch rod, 22,975. That's a lot easier than doing all the math, right? And we got a chart like this too, so there's another chart in here that's got that's got pneumatics. Yeah, so here, this is on page 22. There's page 22. And what's on page 22? This is pneumatic force, right? Yeah, hydraulic, 3,000 psi. We couldn't run air pressure at 3,000 psi. I don't know what pressure it actually turns back into a liquid at. I didn't research that.
So let me ask you a question. So, like when you looking at this, you come and you saying 3 and 4, and you said.
Well, none would be the push, and then your rod would be the pull, right, or the retract.
So whatever side the rod, that's what pick and be.
Yes. Right. So these are rod sizes right over here. Yeah. So this would be the bore. This would be this would be the rod side. So this would be your retract force, right?
No, we don't worry about.
Huh?
No, it's the rod.
No, and that's the push, because you don't have the rod on the push, right? So, you understand what I'm saying about this? So the push pressure, you'd use none, or the push force, you would use none, and then the retract, you would use one of the rods.
Okay.
Yeah, same thing with hydraulics. You said the pressures are going to be, yeah, charts exactly the same.
So the non-number is always a large number.
That is the bore. That's your push pressure. Yeah, that's going to be d squared times the square root times the square root times, d squared times 0.705 times the bore. Now the rod size is the area of the bore minus the area of the rod. Right. Understand. So your retract force is going to be less, but your speed is going to be greater.
Okay. All right. Just need to pause for one moment. I'm trying to understand. I want to now bring the meter out and meter in.
Has nothing to do with it.
Because the push
has nothing to do with it. So you're talking about speed and we're talking about force. Now, of course, when you meter in and you meter out, you're going to change the pressure and you're going to change the force. So what you got to know, when we talk about this is the pressure at the inlet of the cylinder. This is not the pressure on your pressure gauge over there. This is the pressure gauge on your inlet. So if you was going to calculate the true force of that cylinder, you would have to know the pressure available at the inlet of the force when the valve is in motion. Now you got to understand when that valve, when that cylinder hits its end stop, you have no more flow. If you have no more flow, you have no more loss in the system, right? You understand? And you get the maximum force. You don't get the maximum force while that sucker's in motion. Why? Because the fluid is flowing. When the fluid is flowing, you get pressure loss in the system. Huh? Well, that's why you got a hose. You press that sucker like this, and you got all that flow, right? You understand? As soon as you let it go, that hose pipe pops back out there because you have no more flow, right? Now, of course, you can open that thing wide open, and you still have problems pushing in on that side of the pipe because now you're actually feeling the resistance in the flow. But as soon as you stop that water, that pipe pops back out there because you're getting the full flow force. Because as soon as you lose the flow, then all the drops in your system are gone. So as soon as that actuator comes up there and goes into that cushion, it can generate more force, and when it stops, it gets the maximum force that's available from your pump. By the way, the pumps don't create the force. What creates the force? The pumps and your compressor creates flow. What creates pressure? No, you have to run it against something. You don't get pressure unless you push.
You see it.
Yeah.
gotta be that actuator.
Huh? Whatever it runs up against, right? Yeah, whatever it runs up against. Yeah. So wind going across the ocean don't do nothing unless it gets against a sail. As soon as it gets against that sail, now it generates a force, right? You understand? We have work. So when it flows through those pipes, just the side of the piping and going through the orifices in the valves, and a flow control valve, it literally creates a opposition. So we always have a pressure drop across the flow control valve. And the flow is going to slow the flow down, right? You understand? But as soon as that thing hits that end stop, you get whatever you got. Whatever it can give you. So when we talk about this, force is equal to pressure times area, that's the pressure at the inlet, right? You understand that? So anytime we get loss in the system, and you can see the loss in our system over there, I don't know where the compressor's at, but every time so we got our pressure regulator right there, and what happens every time you do something? But as soon as the actuator stops, what does it do? Then it goes back. But what's causing that to happen is the loss in the system, right? Wherever our compressor's at, how far does it got to go? What type of piping do they have? What's the gauge of the piping? What size of it is, right? You understand? How many 90-degree turns do they make? And, of course, most of your turns are okay. They're not. The CD rating. Now, this is something that they give us. We call it the CD rating, but it's actually what they call the flow coefficient. So if you looked it up on the internet, you wouldn't type in CD because you'd get all type of garbage. This is what they call the flow coefficient. And this is basically the resistance of the opposition of the valve. The opposition of the valve. Because if my valve has got a lot of opposition, we're not talking about flow control, we're talking about directional control valve. If my directional control valve has a lot of opposition, we get a lot of pressure drop. If we get a lot of pressure drop, we lose speed. And not only do we lose flow, we lose pressure. We lose force, right? You understand? So choosing the right valve is very, 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 very important. So what we have is what we call a flow coefficient, and we abbreviate it CV. This is the U.S. customary. And then over in the IS, it's going to be metric, and it's going to be called KV, and we're not even going to go over how to calculate The larger the CV rating or the KV rating, the more fluid the valve will pass without a lot of pressure loss. Does that make sense? Everybody okay? Now the math involved in this is not very easy. So this is on your book. I don't know what page it's in. Let's find the CV rating of the valve and help tell me the page. Yeah. The actual formula, this is the actual formula for CD right there. So we're not going to use that. But what they got is that what they've done is they've reduced a lot of math by putting a lot of information in a table. So instead of me doing all these calculating, all we're going to do is just look things up on the table. So we're going to calculate the volume. The volume is the area times the length, right? So that's the first thing we're going to do. We're going to calculate the volume of the cylinder that we're trying to push this fluid into. Then we're going to multiply this times the FA, which they call a constant. So what we do is we look over here in this chart on table 40-42. You notice the right three columns talks about A. And this is how much pressure we're going to lose across our valve. And they gave us three settings. They give us a 10 psi loss across the valve. They give us a 5 psi loss and a 2 psi loss. 10 psi valves would be less expensive because the orifices are going to be smaller. 2 psi valves are going to be very expensive because it's got all the internal porting and everything's really big. If you know the pressure drop across the valve, or you can measure the pressure drop, then that's what you would probably use, right? If we don't know it, then what we do is which one you think we'll choose? 5. So we'll just use 5 for pressure drop. And then we'll always go up to the next CD rating. And that way you know we're going to do a little bit. That makes sense? Yes or no? Huh? Unless I tell you different, we'll use 5 for the pressure drop. And say that's going to give you a CD, that's going to give you a number. So when we go out and buy a valve, somehow I've got it. So this is a typical valve. So this guy here has a CD rating of 1.68 at 80 standard cubic feet per minute and at 100 psi. So 1.68. Okay. So 1.68. So what that means is if I come up here and calculate I need a CD rating of 1.2 or something like that, then this would probably be the one that I buy. Right? So the CD rating is just a number. It don't tell us the flow, but it gives us an idea of the flow. So instead of me trying to deal with all these numbers, if I can understand CD, especially using this table, then now we know what CD rating of these valves we need. So when you start looking at pneumatic specifications for these different valves, that's one of the specifications they're going to tell you is the CD rating of the valve. So what we've got, instead of me doing all this math, then what I can do is I can use this basic formula right here. So what we do is we use 231 for hydraulic, and we use 29 for pneumatics. They're right here. Now what we've got to have, and where these numbers come from, it's actually 28. It's actually 28.8. But most people, instead of using 28.8, they use 29. Because this is kind of a guesstimation anyway, right? Does that make sense? So why use 28.8? And then we just go ahead and round that up.
How come we can't put a gauge at the end of it? Like move the golf and steady the golf.
So here I'm trying to buy a valve. And I don't even have a system to put a gauge across. Now, if there's a valve in there, then I'll buy the CD rating of the valve that's in there.
Oh,
Unless it don't do what I need it to do.
well,
So let's say I got a pressure drop of 20 psi, and I said, well, I can't afford that. So I need to have one with a bigger CD rating. So you say, okay, what pressure drop do you want? And what PSI do? And then you can figure out which CD rating of the valve that you wanted to replace it with, right?
because it's already, because it's already right there. I mean, so the numbers they give us there will tell us approximately what it will do.
What the, yeah.
Okay.
What we want. So let's say we're running 80 psi. Okay, you understand? And I want to so 80 psi. And what size cylinder are we trying to work with? So that's what we're going to deal with. What size cylinder are we going to work with? So when we talk about the valve, we're talking about the flow. The flow is going to occur until that whole volume of that cylinder is filled up. Now, as soon as the volume of the cylinder is filled up, everything stops. Right? You understand? So when we calculate the CD rating, we want to see, okay, how fast do we want that cylinder to fill up?
49 was the hydraulic.
231. Yeah, because what this is, it's in cubic inches. So we got a conversion factor where we can go from, for fluid power is 28.8. And then the pneumatics is, I think I tell y'all this somewhere else. Almost at the bottom of the slide somewhere. Right here. So this is what we're dealing with. All of these are cubic inches per second. So if you went and said what's the conversion factor to go from gallons per minute to cubic inches per second, it would go 231. Of course, gallons per minute is what? Is a liquid, right? You understand? And it would tell you the conversion factor to go from cubic feet per minute over to cubic inches per second. It says the conversion factor is 28.8. So that's where these numbers come from. So instead of these formulas trying to throw all these, they all use cubic inches per second. And all we got to do is figure out, okay, if I'm dealing with gas, I'm going to use 28 or 29. If I'm using liquids, I'm going to use 231. Does that make sense? So this formula sheet that I hand out, it's basically, it says fluid power, but it's hydraulic. So every time I see a 231, if I'm using with pneumatics, I'd change it over to a 29. And the formula would be the same. So that makes sense? Yeah, so all these are in, but the problem is and what it is, it gives us the ability to have a formula, cubic inches per, cubic inches per second. Is that gas or is that liquid? Well, it's either one of them. It's cubic inches per second, right? You understand? So that's why just about all your formulas are set on that. So what I'm saying is, for this one, this is for fluid power. This is for pneumatics. If I was going to take this formula if I was in a hydraulic system, instead of using 231, I would use what? Using 29 and using 231. And the valves can be smaller for fluid than it does for gas, right? You understand that? Yes or no? So first of all, I come up here and I say, I need to know two things about my cylinder. I need to know the area of the cylinder, and I need to know the stroke of the cylinder. Everybody understand that? That makes sense? Everybody okay? So since my volume's in cubic inches per second, then my stroke has got to be in inches. So if you got a 1 foot cylinder or 3 yard, 3 foot cylinder, you'd have to convert that over to inches, right? A is a constant from the table, so if we're not given, we use 5 psi. F is what we call the compression factor. So all we're going to do now is look at the inlet pressure to the cylinder, and then these other numbers are given to us. Right? You'll see what I'm talking about. So I'd come over here and I would say, okay, 80 psi. Then I would use what? 6.4. Are we okay? And then the time for the stroke. How fast do we want this thing to? So we're trying to extend it in what? What do you want to do? There's one on the next page. Y'all got your chart, right? Everybody okay on the chart? Know what these different things are?
Oh, now it's like that.
Okay, we okay?
Wrong.
Okay. So in this example right here, it says pressure at the inlet, we got 80 psi. If not known, use 5 psi pressure drop in column. So that, so if I look at 80 psi and go over to 5, it's going to be 0.048. Is that right? Huh? Are we okay? Because there's one of these on there. For our problem, the cylinder has a 3.5-inch bore and a stroke of 6 inches, and we need to extend an extend time of approximately 0.75 seconds. So that's going to be 3.5 squared because we're dealing with extend, right? Times 0.785. That's going to give us the area, which is 9.2 inches. 9.2 times the length, which is what? 6. That's going to give us the volume, right? Everybody understand that? Times 0.48. That's our compression factor. Times 6.4. I'm sorry, our constant. 0.048 is our constant. 6.4 is the compression factor. And I'm going to divide that by 0.075, which is a constant, right? Times 29. So we need a CV rating of 0.78. I'd probably use 1 or 1, right? And you don't have to use parentheses on that top number. But I just wanted to make sure you knew all that went together. But as soon as you hit that divide, then what are you going to have to do with that bottom number? That bottom number you're going to have to put in parentheses. And that's one of the biggest problems people have. They'll just try to string it out there. And what they'll do is they'll divide that by 7.5 and then they'll multiply the answer times 29. And they can't understand why they come up with the problem. So let's come up with something, then we'll take a break. So what PSI do y'all want to use? Okay, 150 PSI. What cylinder do we want? What bore? What's the bore? Let's use a 2-inch bore. Okay, and what's the stroke? Which 6 inches again? 8 inches. That would be a pretty good deal for a 2-inch bore, but that's okay. I don't know, 2 inch, that 8 inches would be fine. 2 inches is pretty good. Of course, it depends on how size, and all we're going to do is the extend. We're not going to worry about the retract. Because the extend is when you're going to get the most. In fact, I don't even know why I said that. The extend is when you're going to have the most volume anyway. So we wouldn't even worry about the retract. That makes sense? So if we put enough flow in there for the extend, we're definitely going to put enough flow in there for the retract. Anything else we need? I think that's it, ain't it? Huh? We got everything. 2-inch bore, 8-inch stroke, 150 psi. Oh, time. I'm sorry. That's where the .785 came. So time, let's say we're going to do, what do you want? Now, the bigger the time, the smaller the CV rating, right? Because you don't need the fastest flow. So let's just make it easy. Let's just do 1 second. And then let's take a break. Take a 2-minute break. And then we'll work it when we get in. I did roll yet. Oh, really?
Yeah, I don't know if that's what's got the other guy. I had to get off. Almost done.
Take the area, right? So the area is equal to 2 squared times 0.785. And what does that give us? Huh?
3.14.
No, 3. I think say that 2 don't sound right. $3.14. And then I would start off, I'd say 3.14 times the stroke. What's the stroke? 8. Times my 5 PSI drop. What's that going to be? 0.048. Wasn't that right? Huh? Oh, wrong PSI. I'm sorry. You're right. We're doing 150 PSI. Okay, so what? What is it? 0.036. Okay. 10 times our compression factor. What's that? 11.2.
But I'm wrong.
And then divided by 1 times 29. So this is going to be really easy because so all you have to do is just divide it by 29 because the time is 1 second.
My new number gonna be 0.45. 0.45.
Yeah, you'd always go up. What did y'all come up with?
0.349.
3.14 times 8 times 0.036 times 11.2 equals divided by 29. That's it.
You left all the other numbers in. I just want the 10.1. You left all the other stuff.
You went with 10.1.
If you go back a step, you had 10.1259876.
No, I don't want to say that.
3.14. 3.1.
times 8 times 0.036, right? Times 11. Okay.
And then when we 10.125978, you left all that in, where we just did 10.1. They gave us that. Drop.
Yeah, but it wouldn't come up with as big as errors. Like I got 0.3. Y'all got 0.0 from.
Well, we got 0.35.
Okay, good. Thank you.
Yeah. We said 0.35. That's what we did. Not 0.35.
Okay.
0.35.
There you go. That's what I couldn't understand.
Yeah.
35. Well, we would round it up to the next available CD rate. So you can't say I'd round it up to 0.35 because if there wasn't a 0.35 available, then you'd go up to the next biggest available CD rate. That makes sense? Yes or no? Everybody okay? Everybody that's here. Let me rephrase that. I'll go ahead and pause this and do roll. Like I said, that's the actual formula, by the way. That's without the chart, without the tables. Cylinder symbols, are we okay here? There's some that we haven't talked about. These are some simplified signals. But this guy right here, y'all see what that is? Yeah, these guys usually have a little groove or something down one side. Because if you've ever noticed a round piston, a round cylinder, if something wants to move, you can just grab that thing and do what? Yeah, twist it, right? So we do have some cylinders that will not rotate. They're not allowed to rotate. So what usually happens is you don't see it. Inside the cylinder, there's two grooves on the inside, and the piston actually has a groove in it. So yeah, guide rail, so don't allow the what? Turn. And we've already looked at cushions. Everybody okay there? Adjustable cushions. And I've never seen this. I don't know what this is. This is double acting air hydro cylinder with double piston rod. I know what a double piston rod is, but I don't know what they mean. I guess I know what they mean. What do you think it means? Yeah, that's what it means. This cylinder right here could be used for either air or liquid. What was you saying, Franklin? These are the ones that we actually have here. We don't draw them like that, but this is ours. The flow control, the one-way flow controls are actually built into the cylinder. But we just come down and drop ours. We're making y'all use external flow controls, right? But we do have. I don't know if the signal acting cylinder's got flow control in it or not. But we're going to use the external flow control anyway, so they should be turned all the way down. I don't know what a stroke reading cylinder is. I have no idea. Stroke reading cylinder with a brake. No, it's got some kind of dial on the side where you can actually see where the piston is. And that does make sense. Stroke reading cylinder with a brake. That probably is something, a unit in there when you put pressure on it, it releases the brake. We got one of our Traverse robots over there that has a pneumatic brake on it. But it's actually a separate unit. It's actually on the side. Everybody okay with cushions, right? Now ours are a little different because this is a new symbol that's been probably before this came out, where they put that magnet in. They put that magnet on the piston. So ours are actually. So if you looked at the symbol of the ones that I gave out, then that would probably be They don't give us the symbol for a telescoping cylinder. So let's go ahead and I'm gonna go back and see if I got that symbol in here. I think it does. Now the one thing it don't have, yeah, it does. Yeah. Yeah. So this is it. This is a single acting telescoping cylinder, and this would be a double acting telescoping cylinder. Now one thing that the book does not cover, which is becoming very, very popular, is what we call rodlet cylinders. And I need to put that into slide 2 while I'm thinking about it, because we've got rodlet cylinders. Now, how can we make a cylinder rodlet?
Whoa, look at those prices.
Well, cylinders are pretty expensive. So the way the rodlet cylinder works, we got 2 ways. We got where it comes in and literally, let's see, let me blow this up. Let me do this. Still not real good. These are the ones, it might just come up, but it just took us to the website. These are the ones that we got. So what they've got, no, this is not. They got the ones that's got the bands on them. So what you do is you got bands, and then the bands come in through a seal, and then the piston comes in and slides back and forth and moves the bands. The ones that we have, the piston has a big old permanent magnet down here. I mean, we're talking about a big one. And then what happens is the carriage just does what? Latches on that magnet. So when you move that piston inside there, that carriage just slides right on outside. And we got magnets now, guys. We got magnets now that are dangerous. I'll bring one in off a disk drive. Little tiny thing, but it comes off of a disk drive that actually positions the read-write head on the disk drive. And I'll let y'all pull that thing apart. There's 2 of them. So we got permanent magnets now that are just unbelievable as far as their strength goes. They got them that you can't. So the ones we got, you can actually put them on each side of your hand. They'll pull together on each side of your hand.
Get it out of here.
Yeah.
What?
Yeah. Huh? We call them rare earth magnets, so they're not, and they're really nice. They're usually metal, and they are really strong. Which is really nice because I don't know if y'all remember headphones. When I was stereo, our headphones were like these, and the speakers on them was at least that big. Now we got these little earbuds we put into our ear, and they really got good sound because of the magnet, because of the size of the strength of the magnets and the size that we have now. I still like the ones that cover your ear. They're still sound. Oh yeah, I know. I got a pair. Mine's Bluetooth. I love them. I wear them when I'm cutting grass. So we got 2 types. They usually use a band. And what's nice about, what advantage does a rodlet cylinder have over a regular? They're very expensive, but what advantage? They have an unlimited stroke. I mean, you're not sticking a rod out there. So anytime you got a rodlet cylinder, then you got to support that rod when it goes out there, right? You understand that? And then the further the stroke, and the further you get away from that
So
thing,
what we doing, instead of sticking the rod out, we making cap in and head.
yeah, you gotta
extending
take,
that out.
yeah, there's no head
Gotcha.
in, there's
Okay.
no cap in, it's
Okay.
both cap ins.
So the first I was like.
And you can run these things,
Yeah.
it's got an unlimited stroke,
Right.
right?
As
You
long
understand?
as they-
So for extremely long strokes, and you're not generating extremely high force, you wouldn't run into these in hydraulics, but we run into them in pneumatics. Because pneumatics, we're not dealing with extremely high forces anyway, right? Rodless cylinders, let's look at the symbols.
How long can that?
We've got ours, the longest one we have over there is probably about 36 feet. It's one of our robots. Well, the robot's mounted on it. And what it is a sorting, y'all saw it. It's over on the, yeah. I need to add this to my PowerPoint because they're becoming very popular in pneumatics. As I spell rodless right. So that's not a rodless cylinder. This is it right here. So this one has adjustable cushions, and you can see the cushions up there. So this is the actual cylinder right here. This is a double acting rodless cylinder. So you just got that puck in there. You got the piston, the double acting cylinder. All ours over there are double acting cylinders, by the way. You know. So the Festo line has one on it, and the Amatro line has one on it. And these are robots that have to move. They're gantry robots. So the gantry robot is not like a gantry crane. A gantry robot is the one that's mounted on an overhead rail system. That's what we call a gantry robot. A gantry train is a overhead crane, but it's mounted on rails, so it has the ability to roll around on rails. You can see a lot of those. We used to have a U.S. Steel outside. Yeah. So, are you okay? And like I said, that's not in the PowerPoints and it's not in the textbook, but they are out there, and especially in pneumatics. The next thing we look is of course, so we have rod actuators, rotary actuators. Let me get this off in a second. And they all work basically the same way. So what's the difference between a motor and a rotary actuator? It has an unlimited stroke. It's internally unlimited. You can limit it outside, right? Don't understand that, but not inside. This is the symbol for a rotary actuator, by the way. Now this would be a double acting rotary actuator. We do have single acting rotary actuators, where it has a spring that brings it back. Are we okay? These are the different types. We have a helical. Basically what happens is there's a grooves like that, and we put pressure on one side, and when it comes up, what does that whole thing do? The edges spin. This is we got one of them that's like this. So this is a reciprocal, or what they call an enclosed piston, or some people call it a reciprocating. Can you see how it works? As soon as I erase it. Then we have what they call a Scott yoke. So this would be basically a dual piston. So we're just moving both sides. Then we have what we call a rack and pinion. We have a rack and pinion is like a steering wheel. Used to be. So rack and pinion is where you take a rotary and convert it into a linear or vice versa, right? So what we were doing on our rack and pinion and our driving wheel is taking rotary and converting it into linear. We could take the same way and turn the pinion, right? You understand that? You turn the pinion, then the two things move inside. This is we've got this one over on the Amatro line. It flips the shells, the valve shells around when they're in the wrong orientation. And then we have a piston and chain. Now we don't have those over there. The ones we have over there, we have, and there's one that they don't show. And it basically works just like this symbol. But what it just has a vein in here. So it's got and then it's just got a wiper that comes up here. It's a vein. This is the one we have on one of that. And then it comes out right here, and our actuator is actually mounted back in here. So what happens when we push that, put air in there, it just comes up here and pushes against that vein, and then what? Slams up one way. So that's, I don't know why that didn't show up when I researched it. But this is the one we have on the Festo line that's picking up cylinders and dropping them over on the lift of it. But what determines the speed on these guys? Of course, the flow, right? You understand, pressure flow. But what we start dealing when we start dealing with rotation, especially on motors, then we're going to start dealing with displacement instead of cubic inches. Right? What's the difference between cubic? They're basically the same, but when we start talking about cubic inches, y'all know what that means now, right? That's how much air it will displace. On motors, it's how much air it displaces in one revolution. Fluid power motors, those are pretty easy. By the way, the stroke on rotary actuators are given in what? Degrees. Yeah, which makes sense, right? Fluid power motors converts electric energy into rotating and has an unlimited stroke. Displacement is the amount of oil that moves, or fluid, it would be more correct there. So that would be even true. A displacement is the amount of fluid that must be pumped into a motor to turn it what? One revolution. Some motors have fixed displacement and some motors have variable displacement. So if we got a fixed displacement, it's going to create the same torque at the same speed. If we do variable displacement, we're going to get less torque and more. It depends, right? The torque goes down, speed will go up. I understand that. As long as it can turn the load. Motors can be unidirectional or reversible. So we call them bidirectional or reversible. So here's our symbols, guys. The ones on the left are fluid power, are pneumatic. The one on the right are, ones on the left are hydraulic. The ones on the right are pneumatic. And you notice that basically the only difference in the symbol is hydraulic has the era shaded in, and the pneumatics is on pumps, motors, this may or may not be on there. This would be the output shaft. Notice they have it on this one. They could always have it on this one. If you got both eras on both sides pointing in, now pumps and compressors, the air points out. Right, you understand? On motors, the air is pointing what? Makes sense. If it can be
fluid into the motor.
Yeah, because that's what we do. We pump fluid into it, right? That makes sense. So that would be the output shaft. This is a rotary recovery. They call it a partial rotation motor, but this is what we call a rotary. Are we okay? Unidirectional, bidirectional, variable displacement, unidirectional pressure compensated, unidirectional, of course, all these would be pneumatic. Okay. How do we make stuff spin with fluid? Oh, what's this right here? This is just some specs off from some hydraulic motors that we had. I forgot who manufactured this came from. So they give you, these guys can turn pretty high speeds. So that's not too high, is it? Cubic meters, see, I don't know what this is. Liters per minute, PSI, bars, PSI. This right here would be torque. No, I'm sorry. This would be horsepower. This would be pound inches. I'd have to look that up. There's two things. We have what we call foot pounds, and then we have what we call pound feet or pound foot. And those things means different things. I know what foot pound gets, but I get the other one confused. I'll do a little more research on this because I'm the one that put it in there. These are the fluid power motors we'll look at: gear motors, vane motors, and piston motors. And I think we got some gear motors. In fact, most of our motors over there are gear motors. And then we don't have any vane motors over there. I started to bring I've got a impact wrench that broke. I started to bring it in. It uses a vane motor and piston motor. This is the formulas for speed. So what are we doing here? Yeah, 231 times the gallon per minute divided by the what? Displacement. Pneumatics, it's the same formula, but it's 28.8 or 29 times the cubic feet per minute divided by the displacement. And then the horsepower formula, let's look at the horsepower formula in y'all's fluid data book and see what it says. That might be it. I don't think it is. Let's see if I still got it up here. Yeah, I do. The formulas in this book, are kind of hard to find because usually they'll have them down here inside this thing right here. So calculating cylinder speed, and then it'll give you the formula down here. This is horsepower compressed air. What is horsepower? How did they come up with horsepower? Quarter horses, yeah, to pull a weight up, a whale, a certain amount of time. And they did a bunch of them. They got an average, and they came up with this work, and then they could compare that to a steam. And that's what they was trying to do, because people didn't understand what steam. All they understood was what? Horses. Horses. How many horses does it take to do this? How many horses? So that's what they came up with. And then they have to convert that over to moving fluid power and that kind of stuff. So y'all see a formula for horsepower? Where's that? What page is that on? Yeah, so horsepower. So this is what you got on this thing. You got to be looking for, right? So it says to find the horsepower, use the formula. Horsepower is equal to torque times RPM divided by 6252. or torque would be equal to horsepower times 5252 divided by the RPM, and RPM would be equal to the horsepower times this. So this is the actual formula right here. So what is torque?
Torque is like turn something, the pressure of the turn, like motor in the car, like I'm telling the wrench is for a certain torque, make sure it's tight, that pressure that push back.
So what do you do when you do that torque? You got the handle a certain distance away, and you're pulling it at a certain angle, right? So 1 pound of torque. We use foot pounds. U.S. customary use foot pounds, right? One pound of torque, 1 foot pound of torque would be if you had a 1 pound of weight and you had 1 foot distance and then you moved it. So 1 pound of force would move this one at a distance of one foot length. 1 pound of force would move it 1 foot. That makes sense? And so this is what we do with our torque wrench. Our torques are in foot pounds, but what you're doing is exactly that feature. So your torque wrench has got to handle what? So far. And then what you're doing is you're putting so much force on it and you're moving it a certain amount of distance to create this torque. Where at? Down here. Right? You understand? So it's kind of complicated. And of course, that's one of the things that people want to know is how much torque that you have. We know the more torque you have, the more work you have going to your rear wheel. So what we do is, and this is also true in the SI, I mean the international standard, the SI units, is that they don't use foot pounds, which is what we use. Imperial, the imperial standard, which is what they still use over in Britain, they still use it, and then we use the foot pound over here too. So what we need to do, what we'd have to do to calculate the horsepower is we'd have to know what? We'd have to know the torque. But when they calculate the horsepower of a motor, basically, how do they do that? Or when they do the horsepower of an engine, how do they measure that? They put it on the thing, they put the rear wheels down, right? They put it up against a certain resistance. They see how far it turns, how fast it turns, right? So what they're saying right here is that RPM, and then we've got, so what they're doing is they're calculating the torque. So we can calculate the torque using this guy right here. We can say the torque is equal to the horsepower times this constant divided by the what? Divided by the what? RPM. Okay, you okay? RPMs is not plural. No, RPM is not plural. So that says, okay, if I've got, revolutions per minute, but we don't say RPM. So RPM is it's just like people say gigs. So it says, okay, if I've got a 40 horsepower motor and it's running at 100 RPM, then how much torque would it develop? So it says I got a 40 horsepower motor running at 100 RPM. How much torque would it develop? 2100
RPM.
Now what's torque dividend? What unit is torque?
pounds.
Foot pounds, yeah, there you go, thank you. That's the, yeah, never use foot, you ever use torque wrench?
Yeah, but you know, with it.
The horsepower was 40 and what? The RPM was what?
100, I just used the first one.
40 horsepower. 100 pounds.
If RPM goes up, what does torque do? Why? Speed goes up. Yeah, if work is equal to force times speed, right? You understand? If speed goes up, then this guy's got to go down. And that's the biggest thing, one of the hardest things we have to teach is that people think that we get more work out than we put in. But actually it's slightly less, right? You understand? So if we understand that, then we can understand that speed goes up, this goes down, and that kind of. Okay, y'all guys take a 10-minute break. Take a break. Yeah, these formulas in this book are hard to find. I need to. Let me spike this.
Cool out there.
It is.
Are we gonna be in the lab tonight?
Yeah, we know. This is about. Yeah, this is about the time we usually go. I'm gonna see and we're almost through with this lecture.
How many little things in this book you actually, I know they're all in there for a specific purpose, but I'm thinking some of them more used than the others. I'm putting the ones that we use in this class, the ones that we use most.
In this class, it's got a ton of information in there. If you ever get into fluid power, you use a lot more than you use. We teach enough fluid power for you to work on it and understand how it works, but this is not near what there is to fluid power.
Wow.
It is a lot of data information too, and we probably use very little of it. Probably 1%.
Somebody in the natural field?
No, us.
Oh.
In this class. But it helps you size piping, it helps you size valves, it helps you figure out pump horsepower to do what you need to do. It helps you so it gives you a lot of information in there that we don't have time to teach in just one 8-week course. That's why we went to 3 semesters on our program logic controllers. PLCs are becoming so ingrained in the industry. They're in such big demand that we have to teach more than just an introduction. Or you're looking at a fluid power motor. How do y'all think of that? I don't know. It's just that you can get cutaways like that. And it works too, I think, sure. Really? Well, it's not about fluid power motors, but the pumps are the same. So the same motors, we have the same thing in pumps. Same features, we have this reciprocating one that you see there. It's, we have that could be a motor. Is that a pump or a motor? I don't know. Does it say on the back? That's it. Let me see how it works. In or out. You have to get out. You have to get out. Motor, push up on it. Push it against that angle. Cause it to run. And then when it turns, it automatically gets out. That's the pump. Over here, you have a pipe move. Turns it. Causes things to come up. What goes up is such fluid. And then it automatically goes and takes it around. Over here, just about this way. So it looks like this is the valve. So if this was a motor, this would be the inlet. This would be the valve. If it was a pump, this would be the suction.
Making that break. We got to go. Yeah, we all get good. So we help each other out. Taking off.
Still doing it, still doing it here, it's all come back to you.
So your maker says yes. So what made you decide to take this?
I mean, yeah, I thought it was about it. So,
Well, you understand
system and pressure.
the pressure and the evaporator and the condenser.
I mean, so far, I see it related. You know,
Probably, of course, in PLC. We're going to work on big commercial applications. They run like PLC. Yeah, we are, right?
oh, and not here.
No, it's your day. Yeah, so commercial applications, most of them run PLC. The control is not that complicated. They're not.
Oh,
I mean, PLC. Residential. But my unit has got one of those things, I forgot what they call it, it's electronically controlled motor.
Yeah.
You don't have a relay on it. I've already lost two of them. Luckily, it's still, huh?
If that,
You get one?
You ain't know.
All right. I thought,
He didn't give,
did y'all bring them back up here?
he didn't give me but 3 of them. What's the 3 of them?
Oh,
you back.
it's up there somewhere. Here. Yeah, these will just help you, in your design, do stuff at home so you know what you have. So eventually, especially, I think it's, assignment number 4, y'all gonna do your design at home. For the final layout, which will be, and we'll set up the flow of the class. And this, y'all can have these too. What are these? These are, what you can do is, every place that says 231, every place that says 231, you can change it to 29, and that would be, pneumatics, right? Y'all understand? So these formulas are both good for pneumatics. It says fluid power, but the only thing they give you is the formulas for hydraulics. And y'all can use these on tests too. Of course, it don't have the Pascal laws or the Boyle's laws or anything like that on there. I should have ran off some. So y'all got any questions so far? So this is basically, we'll probably, I need to lay out the rest of the semester.
As far as the book concerned, this book right here, we don't, only thing we have to worry about is what we go have.
Okay.
We put a little check mark by the section.
Or highlighted, or if you got your highlighter there. It works out really, really good for all those forces. Instead of having to do all that math on those cylinder forces, and of course they don't have the CD table in there. That CD table is in the textbook. They don't put that in there for some reason. They give you the long math on how to calculate the CD inside that little data book. I don't think they give you anything on a shorthand method for the CD in that book, do they? I didn't think I even saw the CD rating of the valves in here myself. Interfluid, pneumatic force, speeds for fluid flow at 25 to 100 gallons per minute. Now, they basically just forgot about pneumatics when it came to cylinder speed. But they've got some pretty good charts in here on hydraulic cylinder speeds, where you got the gallons per minute, and then you got the rod, and this is in so hydraulic cylinder feed, gallons per minute, and what's the speed in? Does it tell you in that chart? So this is in page 17. But what's the chart? What's the speeds in? These figures are extensions, force, no piston, rod diameter is involved. Figure body chart or cylinders, piston speeds in inches per minute. So see, this does a lot of math for you right here. See what I'm talking about? Yes or no? So what page is this on? 17. So if I said, but these are hydraulic. So it said if I've got a 3-inch, if I've got a 3-inch bore with a 3 gallons per minute, then that thing would move at 98 inches per minute.
We would need the formula to change it to that.
Yeah, because we don't have the chart, right? You understand? There's no chart in here that you can look up the speed of a pneumatic. You'd have to have the formula to guesstimate. You know, the speed of pneumatic cylinders are basically a guesstimation, right? Because we have a lot of loss in the system. I think I was read it's like a 10-to-1 ratio of the horsepower in relative to the horsepower out. So it says it takes like 30 horsepower of energy in a pneumatic system to get a 3 horsepower of work. So one of the big advantages of hydraulics is that it's a lot more efficient than pneumatics. The big advantage of pneumatics is its safety, right? You understand that? And its cleanliness, its safety, and it's a lot cheaper to install. It's a lot cheaper to install, but over time, it's a lot more expensive to run a pneumatic system than it is to run hydraulics. And hydraulics, we've always got to worry oil all over the place, right? The pressures are so high, it's dangerous if you get leaks, if you get grease on oil on the floor. Then Nancy, for some reason, one of our hydraulic pumps on the Festo line has got a leak on it. It's got that leaking that oil out. He's been over there trying to clean it up. It got on the floor, and even the floor looks like it's clean, but you're gonna have to get some soap and water over there, good soap and water, to clean that up because it's real slippery. So anybody tells you that pneumatics is cheaper, the only thing pneumatics is cheaper is when you do install it. It's a really cheap system because you don't have to return to anything. You just send it back out to air. We use plastic piping. The cylinders are either made out of plastic or they're made out of aluminum, which is a lot cheaper than steel, right? Seals don't have to be near as good, so we run it at a lot lower pressure, which of course makes it safe. But it's spongy. That's one of the problems. Calculating speed is very hard. Force, you got to have a real large overhead for it because as soon as it tries to move, it wants to uncompress, right?
Here, or I heard something kick off or something.
That's the wind blowing clouds.
I don't think so.
Even that's just the alarm to go home.
I think they told y'all they do GED classes here free, right? And it's right next door. That's all the people next door with. They're doing the GED. So if you know anybody that wants these GED, now you have to pay for the test. You have to pay to take the test, but taking the class.
This guy got a big hole of testing.
And you can go to a 2-year college with a they don't call it GED anymore. They do call it GED, but they call it high school equivalent. So we'll look at this motor and then we'll go ahead and go to lab. So a motor, and this is used predominantly in hydraulics, but we could also run into it in pneumatics. This is called a gear motor. Of course, that's the camera. So our motor, I'm almost sure, is a gear motor. And what it's got is got 2 gears that are meshed together. And what's neat, and this is what I was telling Omar, is that the same motors, we have the same pump. In fact, a lot of times we can run a So you have a pressure side and you have an exhaust. Well, I'm sorry, this is a motor. So we have a pressure side and an exhaust side. So we put pressure in, comes in, hits those gears, pushes against the blades of the gears. The big gears come around, seals against the side. Can't get through here. The pressure can't get through here because of the meshing of the teeth. So it comes in, and what does it do? It creates pressure against these gear faces right here, or these teeth on this side, this teeth on this side. The motor turns. Normally, one of them is called the driver gear, and then one of them is called the driven. So only one of them should be connected to the shaft. Then it moves around, gets on this side, and then we have an outlet right here, and then it vents, and then can't get back through here because of the meshing of the teeth. And so what happens is these gears are spinning. Right? These are very efficient method of doing it. Huh? Yeah. Well, yes, but it wouldn't work without the driven, right? Because that's what's actually doing the seal. But yeah, the drive is on this, but this guy right here sees the same thing, right?
Do they have like an alternate oil or something that makes all metal like super slick so these things turn real good? You know, cause less friction or real.
It uses hydraulic fluid.
Huh?
It uses hydraulic fluid.
Well, there's several kinds of hydraulic.
Right, and what determines what some of the things you look. What's some of the things, viscosity, so what temperature, or the mean temperature that you're going to operate the system, right? And then of course, where is it going to be at, and how's it going to, there's a lot to choose in hydraulic fluid. But most hydraulic fluids are, so if I was going to operate inside a place that makes food, then it's very popular to use vegetable oil as the hydraulic fluid. You know why is that? Yeah, I won't contaminate everything if it gets in. I get out there on an earth moving machine, then odds are we're going to have a lot of lubrication and all that other kind of stuff, removing some heavy stuff. So it all depends on the application and what you're going to use that, what you're going to use. Most oils lubricate really good. Now that's why that's one of the reasons you have less loss in the flow, right? Air creates a lot of friction, believe it or not. I mean, you see things that just get flat wore out because of air moving across. So let's go ahead and so we're going to look at gear motors. We'll look at internal gear motors. We'll look at vane motors, which is odds are if you got an impact wrench, that's what it uses. Then we'll use piston motors, which is what this yellow thing is right here. And it's really neat the way it works. And we'll see how that works. We'll look and see how we can do variable displacement. Because if we can change the displacement, if we can change the displacement, we can change the speed, right? We can change the torque and we can change the speed. We got a couple of these piston motors like this that are variable displacement. All we do is change the angle of what we call the squash plate or the swash plate. And we'll look at how we can do that. I don't know of any gear motors that are variable displacement. These guys right here though, this has a fixed angle. But if I could come over here and change that angle on the back right there, then I can change the displacement. Vane motors, we can have variable displacement vane motors, but I've never seen a gear motor that has a variable displacement. Because there's no way in the world you can change the size of the gear. Okay, you understand? These guys here use pistons. All I gotta do is change, if I can somehow change the stroke of the piston, if I can change the stroke of the piston, to make it longer or shorter, then I can change the displacement. And we'll show you all a couple of ones we have over there where it actually has a variable displacement on these guys right here. It's really neat to see how it works. And all they're basically doing is, this has got a fixed angle, so it's got a fixed displacement. But all we got to do is change the angle between the front and the back, and that'll change the displacement. that changed the length of how long. I might give you a smart remark, but I'm not good. I don't.
Is somebody working on the fact about creating something that put more energy out than you put in?
That's impossible.
But it's theoretically.
It's not even theoretically possible.
I'm just saying it's cause we got people working on everything.
You got stupid people working on it. It is totally impossible to get more out than you put in. It's against the laws of physics. In fact, we don't create energy. All we can do is take energy that's already here and change its form. And you always have loss in any system. Even in stereos, it takes more watts in than you put out. I mean, it's always true. There's nothing that's 100%. There's nothing that's 100% efficient.
Well, the only thing I can think is well, the only thing I can think against that are bombs. I mean,
Energy in equals energy out. I mean, you have to put that energy in to get that energy out. And that's all they're doing is taking energy that's already there and changing its form. Like I told you, you can look on the internet. You can look on the internet. I saw one video where a guy had a motor and a generator. And he got the thing running and he unplugged the motor. And he said, well, it's running off the generator. And I knew right off the bat. And I had a guy, and I don't think I ever convinced him of this, but I tell the story all the time. They have these electric forklifts at their plant. He said, Rick, I'm gonna put generators on the wheels. So that when they're out there riding around, they're gonna be charging the battery. And I said, the batteries are gonna run down fast. Because if you get 100 watts out, you're gonna have to put 110 watts in, right? You understand?
Yeah, because on cars more drag.
Yeah. Now they do a neat trick on cars. A lot of times they have on these hybrid cars, they'll have generators on the wheels. They switch them in when the car is going downhill. So as soon as the gas starts letting off, they'll backfeed off those generators on the wheel. And they use those to charge the battery. So what they're doing is they're using the power or they're using the energy of gravity. But energy out is, power out, work out will always be less than work in. Yeah, work out will always be less than work in. Power out will always be less than power in. It's the same thing. So it's basically the formula is power in, power out equals power in times efficiency. And efficiency is always going to be less than it. So let's go lab, guys. That's a good question. And that's a question that pops up all the time. People get some. I had a guy. He actually got a patent on it. He thought that he could take a reciprocating engine and use the upper stroke of the engine when it hit the top to cause the thing to move. And he thought he could just point the thing anywhere, and make the thing go. And this is like people that think they can put a fan in a sailboat and point it put a fan at the sailboat and point it at the sail and cause the thing. Because you always gotta to create motion, you gotta push against. Always gotta do what? Push against something. Because you gotta have equal and opposite. So yeah, I don't think I ever convinced you that. But anyway.
It's just one of those things, if you ever master it, you'll make billions, not millions of dollars.
No, if you ever master it, we'll be praying for you. So you'll be God.
I'm gonna tell you the truth. You ever